In the second part of today's lecture, we're going to focus on how populations grow and look at one model for how populations grow called the exponential growth model. So as we start off with in thinking about these equations, we have things like population and time, and we'll represent changes in population as delta n, changes in time as delta t, and we usually set the t increment to be 1, as in 1 year. And so we have delta n over delta t equals a rate of growth. And we want to figure out what that rate of growth is. So we need to figure out what delta n is going to be in a given year. So as we think about what makes a population change, we have two main things that impact a population. That's births and deaths, births being positive and deaths being negative for a population. We also have immigration and emigration. And those, similarly, one is positive and one is negative for the population. We're going to ignore immigration and emigration for most of the stuff that we do today. So if we wanted to look at this, though, delta n for a given time period is the number of births in that time period minus the number of deaths in that time period, plus the amount of immigration minus the amount of emigration. And delta n, delta t is the change in population per unit time. And as I said, we're going to ignore immigration and emigration and work on what's called a closed population. So that's what ecologists call a closed population, where we don't have immigration and emigration, because that complicates our growth models. So if we look at births and deaths, the total number of births for a population then is going to be the babies per individual times the number of individuals in that population. We can use little b for babies per individual or births per individual, and n for the population. So b times n would give us our number of births. Similarly, deaths is the probability of dying times the number of individuals, and we'd have d and n, and the d times n would give us the number that died during a given time period. So if we think about this, what happens when b is greater than d? Okay, the birth rate is greater than the death rate. And you've got four options. The population grows, shrinks, stays the same, or goes extinct. So you can think this through. If there are more births than deaths, then you're going to have individuals added to the population, more individuals added each year that survive than die, and the population will grow. Okay, so if we take b times n to get our number of total births, d times n to get our total deaths, we can figure out our growth rate then by taking that total births minus total deaths. So b minus d times n gives us that population growth, that amount of change that there's going to be in the population in a given time period. Okay. Remember, delta n, delta t is that change per unit time. And so we could have delta n, delta t equals b minus d times n. Now, we can ask another question here. What's going to happen when b equals d? If we go back and look at this, if b and d are the same number, that becomes 0 times n. So what you should conclude there is when the birth rate and the death rate are the same, the population will neither grow nor shrink. It will stay the same. So if we want to simplify this, we can simplify b minus d down to a single variable that we're going to call Rmax. And if we look at our Rmax and we want to figure out delta n, delta t, we can take that equation that we had b minus d times n, and now substituting Rmax for b minus d times n, we simplify that down to Rmax times n. So that's our change in population in a given time period. And Rmax is called the intrinsic rate of increase. So how do we figure this all out? We can have n sub t, which is the population at time t. We can look at how much it's going to grow. And then what we have at the end of that is n sub t plus 1. All right? So we know that delta n delta t is R max times n, so that's going to be part of this equation. And if we want n sub t plus 1, we take our current population and we add to that delta n delta t. All right, so let's do a calculation of this. If we have n sub t equal to 500 and R max equals 0.5, delta n delta t is going to be our R max times our n sub t, and that's going to be 500 times 0.5. So delta n delta t will give us 250. So we had a population of 500 and our growth is 250, but we have to take into account the original population. So we take that n sub t, which was 500, plus the 250, and we get n sub t plus 1 equals to 750. This is called exponential population growth. And so delta n delta t equals R max times n. Sometimes you'll see this as dn dt equals Rn, and this is a differential equations version of the same thing, which runs on a continuous rather than an iterative process. And exponential population growth is really only observed under ideal conditions. Things have to be very good for exponential population growth to occur. So let's look at this here. We're going to do population growth with R max times n. And let's take a look at what the curve is going to look like. So here we have an R max of 0.5. And if we look, the population will go up at an ever increasing rate because each time it increases, you're multiplying 0.5 times a larger number to get the next year's population growth. So that is what exponential growth looks like. Now, if we are to double our R value, what we see is we get even faster growth. You're increasing the amount that the population will grow each year because you're adding a bigger number to it each time and then starting with another bigger number, moving to the next. So when is exponential growth observed in organisms? Well, we find it in a variety of situations. One is that when organisms colonize new environments, such as weeds growing in a vacant lot, you will see exponential growth in that type of population. The other is introduced species colonizing a new environment, or bacterial infections colonizing your body. Another place that we see it, surprisingly, even in an organism like elephants, is when a population is rebounding. So if we look at Kruger National Park in South Africa, this is an area where historically they practice an elephant cull to keep the population at a low level so that it wouldn't cause a lot of damage to the ecosystem. In 1994, they stopped the elephant cull, and what you see is that the population rose exponentially after they stopped the elephant cull. Very rapidly, the population grew after that. It continues to grow and is quite problematic now. So that's an example of a place in nature where you might see an exponential growth over a short time period. Obviously, elephant populations can't grow forever because if they did, there would be far too many elephants. So how extreme can exponential growth get? So here we have the American robin, a bird that we all know. They will have 4 to 5 young per year, per brood, and then 2 broods a year, so up to 10 offspring per year per pair. Now, if we start with a single pair of American robins and look at what happens over time, within 25 years, you'll have a population exceeding 1 million birds just from that original pair. Now, obviously, not all of the offspring survive, and the population can't continue to grow at that rate. So with American robins, this is the potential for growth, but what we see in nature is that growth does not typically follow exponential growth curves for long periods of time. And in the next video segment, we'll talk about a more realistic model for modeling populations in a finite space.